Now we're going to talk about one of the most important linear algebra operations, which is the determinant. Now I don't want to lead with the formula for this. Determinant formulas are very long and complicated. You can prove why it has to be that formula, but it's an incredibly tedious proof. And it's much more important to understand the geometric picture of where they come from. So in one line, the determinant of some linear operator A is the volume of the unit cube, the cube defined by your x, y, and z basis vectors, and any other basis vectors you might have if you're in a different space, what happens to those after the transformation. So if we have an xy grid that looks like this, my unit cube looks like that. And when I do my transformation, and now these turn into something different. Let's say that the x unit vector is now stretched out that way, and the y unit vector is stretched up that way. And you want to turn this into a parallelogram, or something like that. In higher dimensions, it's called a parallel pipehead. And if I move this up there, and if I move this over there, now all the space inside the volume of this is my determinant. But there's another important element to this, is that the sign flips if you flip the orientation of the basis vectors. So that means if you have a here and then y, this maintains the same, x here and then y, that maintains the same orientation as you had originally of x and then y. But if I swap the orders, if I have a new transformation called b, and b is going to make something where, let's say, x is now over here, and y is now right there. I can, again, fill this out into a parallelogram. I take the volume, and that volume inside is det of b, and that's a negative. So importantly, the determinant tells us information not just about the volume, but about if the orientation flips, if we're now doing this the other way. If you integrate over x and then y, or y and then x, are you going to have to flip some signs if you do some change of variables defined by some transformation like this? So the fact that the determinant is a volume is why it shows up when you do a change of variables in a multiple integral. It has to tell you how your unit cube has been resized. Integrals are all about measuring things with little rectangles or little cubes or things like that. That's why under u substitution, you have to change your dx to some factor times the du. Now it's the same thing here. Now that volume factor isn't just about the width of a rectangle, but about the size of multiple variables defining your rectangles, and that's why you need a determinant. You can prove properties of determinants through some very hard proofs. You can eyeball them pretty easily geometrically, and that's what we're going to talk about right now. So the most important rule is that the determinant of two linear transformations multiplied together. This just means I do B, then I do A. So what happens to the volume of my unit cube is that first, the volume changes by some B. Then I'm going to change it again by A. Those volumes stacked on top of each other multiply. The volume of the whole thing together is the volume of those effects multiplied together. So the determinant distributes over multiplication. This is going to be one of our most important rules. So I am going to give you a few determinant properties. Some of them I'm going to prove for you in the next video. Some of them we won't discuss until you get here in September. But I want you to at least attempt all of these before moving on to the next video. I want you to get used to thinking of the determinant like this. So one of these properties is I want you to guess for me what the determinant of the inverse is. You probably already know this one, but I want you to be able to justify it for me in terms of these volume ideas, or using the properties I've already given you. And there's an important catch to that. What if the inverse doesn't exist? This has important clues about what if a determinant of a transformation is a certain thing that clues you in about the inverse. I want you to work out what the determinant of a diagonal matrix is. If R is a rotation, I want you to refer back to previous videos for what property that has. Tell me what the determinant of R has to be. And then I want you to tell me how we would evaluate the determinant of what we call a block diagonal matrix. So here I have some let's make sure everything's square. I have some square that is a bunch of entries. I have another square that is a bunch of entries. And then the off-diagonal pieces are zeros. So this isn't a diagonal matrix, but you can block it out into diagonal things. And then for the last one, I want you to prove that the determinant doesn't change under a change of basis. This is one of our most important determinant properties. If the determinant doesn't change under a change of basis, then it's coordinate independent. No matter what coordinates you pick, this is always going to be the same. So this is one of those big invariant characteristics you want to hone in on. All right, in the next video, I'll show you how to do a few of these.